Okay, so next we're going to talk about the different fundamental particles, subatomic particles that are relevant to chemistry. And the three that you all are very familiar with, right, from general chemistry, um, are the electron, the proton, and the neutron. Okay, and so uh, you know, here the different symbols, the mass, these are in atomic mass units, so it has a value in kilograms, but a proton is about equal to 1. Notice that a neutron's a little heavier. And then the mass number, okay, so proton and neutron are about the same mass number when we're just counting, okay, approximating it. And then, of course, the proton and the electron have opposite charges, and they all still have a spin of 1/2. First thing I want to have you think about for a little bit, or we're going to discuss, this would be a question if we were in a normal classroom environment, is why is the electron negative? Why are electrons negatively charged, and why are protons positively charged? Have you ever thought about that? I mean, you learned that, obviously. People told you that, but you should think about what you learned. And so why is that? And what if I called protons negatively charged and electrons positively charged? Well, it actually doesn't matter, okay? It could have been that way. We could do that, and it would confuse a lot of people, but it would be fundamentally valid. I mean, the whole idea of negative and positive, those are just names, right? Those are just names. We could have called it black and white, or up and down, or Billy and Bob, whatever, right? So fundamentally, it doesn't matter. Okay, there's some confusion about this though. And for those of you who have taken physics, okay, most all of you have, you'll learn that the flow of current, right? You think of electrons being associated with current. Flow of current is the flow of positive charge. That's how it's defined in physics textbooks. Chemists, we like to think about it as electrons, but electrons are negative, so shouldn't the flow of current be negative charge? Okay, so where did all these discrepancies come about? Well, this is details of the history of science, okay? And Benjamin Franklin, a great early scientist, he did this famous experiment one summer day during a thunderstorm where he flew a kite. This is a great experiment to not do with your kids, right? And he flew a kite, lightning hit the kite, and then he transferred this electricity to this jar. It's called a Laden jar. And basically, he was the first to prove that he was able to store this electricity in here. He was able to prove that lightning is electricity. Lightning is a manifestation of electricity. Okay, so he started getting really interested in electricity, and he is the one who defined the flow. He did static electricity experiments. He's the one who defined the flow of current as positive charge, okay? But he had no idea of what an atom looked like. This is 1752, guys, right? Plum pudding model even, which is an inaccurate model, right? Didn't exist yet. Periodic table didn't really exist yet, right? All of these things he didn't know, so he was just called it positive charge, flow of positive charge. That's how he started doing it, right? And then when J.J. Thompson came around much later, British scientist, right? He basically the father of the electron, okay? He discovered the electron through some cathode ray experiments. He defined things the electron as negative, okay? And so that's where you got this discrepancy. But Thompson could have called it positive. Franklin could have called flow of current negative. It's arbitrary, of course. That's the first thing I want you to realize is a lot of is in science and in life to realize what things are just conventions, right? And what things are actually reflective of some deeper fundamental truth. The fundamental truth here is that electrons and protons are opposite in this charge way, right? And that is manifested in a lot of different experiments. All right. What else? The masses. Okay. I mean, it's just incredible. Why is the universe this way? I don't know. Okay, nobody knows. But the electron, same charge, same magnitude of charge, right? -1 versus +1, but way less massive. Okay. And so To put this in perspective, it's like the electron is a penny and the proton is a huge bowling ball, right? And the neutron is too, right? So that's sort of the order of magnitudes. We're talking about 3 order of magnitudes different. What else? Neutron versus proton. Interesting, the neutron is a little bit heavier, 0.14% heavier than the proton. And I want to just go in a little bit of an aside here about neutrons, okay? Neutrons, of course, are isotopes. So throughout the course, I'm going to try to just throw in a lot of different factoids because sometimes people don't talk enough about factoids and just interesting things about chemistry. And this is part about what makes chemistry so interesting, is that it's applicable to so many different things in our modern day lives. So, I'll very frequently go on these little mini tangents just to tell you about something that I think is interesting about chemistry. So, what are interesting about isotopes, right? You know that isotopes are elements defined as same number of protons, but isotopes are elements with different numbers, atoms with same number of protons, different number of neutrons. So for the case of hydrogen, right, you have proton, protium, that's with no neutrons and 1 proton. Then you got deuterium, that is with 1 neutron, 1 proton, mass number 2. Tritium, by that point, it's not really very stable, so this is radioactive, it falls apart, but that has a mass number 3 because that's 2 neutrons and 2 protons. Those are the 3 isotopes of hydrogen. You got to know that. That's fundamental, basic chemistry stuff that you got to know. So what about if you make water molecules out of hydrogen? We know water is H2O. So normal water, most water looks like this, right? Both of the isotopes are a protium, right? What if you substitute out those protiums and put it in deuteriums, okay? That is called heavy water because it is actually heavier, right? It has an extra neutron in there. So chemists will often call this D2O or heavy water. Now D isn't technically an element, but we kind of break the rules here, and D is used as a layman's lingo for 2H, right? Mass number 2 for deuterium. So D2O is heavier, and there's a lot of very fascinating properties about D2O, heavy water, versus H2O, light water. One is that heavy water ice cubes will sink in light water. So if you make a heavy water ice cube, it's going to look just like regular water, but it's going to sink, okay, in regular water. And why is that? Well, that's because D2O has different physical properties slightly than H2O. And so if you freeze it, it's going to have a density of about 1.1. So things that are more dense sink if they're in liquids that are less dense than regular water, right? Which is about 1 gram per milliliter. Other properties are slightly different. Okay, their boiling points, their freezing points, and their viscosities. Okay, so you can see a higher boiling point. D2O molecules are attracted to one another a little bit more, so it boils at 101. Recall, of course, that this is 100.00000 exactly for water and 0.0000 exactly for the freezing point for water, for light water. Why? That's how the Celsius temperature scale is defined. But viscosity too. It's a little more resistant to flow, D2O, because it's heavier, more intermolecular forces. pH is different, okay? So a lot of fascinating things. So for an extra credit point, if you're listening to this video and you want extra credit, email me a way, you can look it up or hypothesize about it, a way that you can separate D2O, basically enriched water. This D2O, there's natively, right, a small percentage of D2O in all H2O. How you can enrich regular water and make heavy water, okay? And you could actually do this in your kitchen, okay? There's a lot of different ways to do it, but there's a couple of ways you can do it in your kitchen, which is kind of interesting. Don't drink the heavy water though; it's not good for you. It actually can cause cancer and stuff. And that's all we think. People think that. Tastes the same though, according to other people, not me. And what about halfway through, right? Well, then you got dope, right? Which is particularly funny because if you've ever watched The Simpsons, you know that Homer is works at a nuclear power plant, right? And nuclear power plants use heavy water all the time for various reasons. You can look up about why too, but pretty interesting. But yeah, you can have semi-heavy water, which would be one DOH, right, or HOD.